Welcome to Recursion in Python. My name is Christopher, and I will be your guide. In this course, you will learn about recursive functions, how the stack works, factorials, traversing trees, and quicksort. Nothing in this course is very version specific. There are a few F strings kicking around, but besides that, all the code would even work in Python 2. The code in this course was tested using Python 3.11. So, what is it? Well, a recursive function is one that calls itself. That can be a little bit mind-blowing, but there are some specific uses in coding where recursive code is simpler to write and read. My personal favorite is traversing data trees. Next up, I'll get started by showing you an example and how a recursive function works. In the previous lesson, I gave an overview of the course. In this lesson, I'll be introducing you to the concept of recursive functions and how they work. To understand recursion, first you must understand recursion. I really wish I could take credit for that. I used to actually have it on a t-shirt. I don't know the source of the original quote. In mathematics, a recursive relationship is one defined based on itself. The definitions of many fractal functions are recursive. An example of this in real life is the definition of your ancestors. Your ancestors are your parents plus your parents' ancestors. Ancestors is in both the definition and the algorithm for calculating the value. In programming, you do this through the use of a function that calls itself. Consider the countdown function. It takes an argument n, prints it out, and then calls itself with one less than n. It is recursive. So just how does that work? Well, when you call the function with an argument like 2, this gets encapsulated in a little chunk of memory called the stack. The stack is separate from where most things get allocated. The place for everything else is called the heap. The stack is only used to track the calling order of functions and their local space. As a new function is called, a new frame is added to the stack. When a function finishes, the frame gets popped off and the program returns to the calling place of the parent function. This is a bit of an oversimplification, as Python uses references and the stack can contain things pointed to the heap, but it's close enough for our purposes. When countdown is called with 2 as an argument, a new stack frame is created with space for local variables and the arguments to the function. As countdown doesn't have any local variables, that's empty, but it does have an argument. N is 2. The function runs, and the first instruction is called print. That prints the value of n, which at the moment is 2. Next, the if checks if n is bigger than 0. It is, so countdown is called again, this time with the argument of n minus 1, which would be 1. This causes the stack to get pushed down, and a new frame is created. In the new frame, the argument list contains n equals 1. The function proceeds the same as before. It doesn't care who the caller is, just the local state, and n gets printed. It's still bigger than 0, and so countdown n minus 1 is called. Once again, a new stack frame is created, and again print is run, outputting 0. This time, though, n is not greater than 0, so countdown doesn't get called again. This is the end condition for the recursion. If there had been code at this point, it would have run, but there wasn't, so the function finishes and returns. Even if you don't have a return statement, the same thing happens. It just returns none automatically. When the function returns, the stack frame gets popped, and you're back where you came from. There's no code after that, so once again it returns. Then the stack frame gets popped. You're back where you came from. Once more you're done. And then, in this case, control is returned to the REPL because that's what called the original countdown 2 in the first place. Okay, so that was the how. What about the why? Well, there are a family of problems in computer science where recursive algorithms are easier to read and write than their non-recursive equivalents. For example, traversing tree-like structures, sorting, and fractals. In fact, there are programming languages that use this mechanism as the basis for their building blocks. Lisp is one such language. Anything you can code in recursion can be done instead with loops. The code might be easier or harder to read, but you can do it. And the reverse is true as well. Anything you can do with a loop, you can rewrite with recursion. For my CS geeks out there, Lisp and languages like it are Turing-complete, so anything you can code in Lisp with recursion can be done in any other Turing-complete language. It's kind of the definition of Turing-complete. What about Python itself? Primarily, I find I end up using recursion for traversing tree-like structures. Sorting is built in, so you don't have to implement it yourself, and it has functional programming features as well. So the primary use I find I have to code is traversing tree structures. Let's shake off the abstract stuff and write some Python. Next up, I'll show you how to code a function that calculates factorials. In the previous lesson, I showed you how a recursive function works. In this lesson, I'll be using recursion to define a function that calculates factorials. Before getting to the fractal code, let's talk about the limits of a stack. Unfortunately, computer memory isn't infinite, and in fact, typically the call stack is given very little space, as you want most of your memory to be used for your heap. If your recursive algorithm doesn't implement a stop condition correctly, it can run forever, kind of like a while true. But Python's got your back. It imposes a limit and throws an exception if you exceed it. Let's go see this in the REPL. I'm here in the REPL. Let me write a function. Seem familiar? Almost like before, but this one's got a bug in it. There's no exit condition. What happens if I run it? The correct version from the previous lesson ensured that the counter stopped at 0. This one doesn't. After a while, Python sees that this isn't going to end and throws a recursion error. If you're curious why that -993 shows up after the exception, it's because print buffers output. The exception triggers the print buffer to be flushed, but it doesn't happen until after the stack traces output. You can determine the current limit of the stack from the sys module. The default value is 1000. The sys module also has a way of setting the limit. You can tell this is some old code, as it doesn't use the naming convention that is done now with underscores between the words, lovingly known as snake case. Calling set, I can set the value, and when I rerun the function, it blows up far faster. Okay, factorials it is then. What's a factorial? Well, it's a math thing, where n factorial is defined as the multiplication of all values between 1 and n. For example, 5 factorial is 1 times 2 times 3 times 4 times 5, also known as 120 to its friends. Factorials get really big really fast. One of the common places they show up is in probabilities. Consider how most lotteries work. You have a bunch of numbers, and you pick some subset. For some reason, having 49 numbers and picking 6 of them is a popular combination. There is a probability function called choose that is the number of combinations you can select from a set of numbers out of a larger set without duplicates. This function is denoted capital CNR, or sometimes NCR, where N is the set of the population and R is the subset being chosen. It is also denoted as N over R in parentheses. There's lots of choices for choice. The formula for the number of combinations is n factorial divided by r factorial times n minus r factorial. My home province has 2 lotteries, one of which is the common 649. Let's plug in those numbers to see how many combinations there are. 49 factorial on top and 6 factorial times 49 minus 6 factorial on the bottom. The trick if you're doing this by hand is to remember that 49 factorial is actually 43 factorial times 49 through 44. Once you see that, you can cross out the 43 factorial in both the numerator and denominator, giving you a much easier problem to calculate. Or you can use the NCR function on your scientific calculator if you prefer. All told, there are 13,983,816 ways of choosing 6 values from a set of 49. That means winning the jackpot, where you selected the same 6 choices as the lotteries, has about a 1 in 14 million chance. Probability is fun. If a 649 lottery ran every single day and you played every single day, on average it would take you over 19,000 years to hit the jackpot. If the tickets cost $1, you need the jackpot to be almost $7 million just to break even. And the important part of that last statement was on average. Of course, there's no guarantee. By comparison, I found a bunch of different statistics on the likelihood of being killed by a meteor. Depending on whose numbers you believe, you're somewhere between 10 and 20 times more likely to die from a meteor strike than win the jackpot. I mentioned my province runs 2 lotteries. The other one is 7 choose 50. That's almost 1 in 100 million. To put that in perspective, you're 20 times more likely to be killed by lightning on one of your birthdays in your lifetime. Yep, and I still occasionally play. Price of a fantasy rather than a tax on not understanding the math. Let's go play with factorials in the REPL. I'll start by writing a factorial function. And a print statement to help me see what's going on. And this rather compact statement is the actual work. If n is less than or equal to 1, return 1. Otherwise, return n times a recursive call to factorial with n minus 1. Another print statement to see what's going on. And return the result. Let me try this out. Notice what happens here. Because the recursion is called before the second print, you keep getting the first print called until the end condition is met. Once the end condition is met, the stack unravels, and then each function returns to its calling point. It is from there that the second print gets invoked. The deepest call returns 1. The second deepest returns 1 times 2. The third returns 2 times 3, and the last returns 6 times 4. This file contains 3 different ways of achieving the factorial, allowing me to compare the performance of each. The first is the one you just saw, but without the print statements. This is the recursive version. The second uses a loop instead, looping over the range of values from 2 through to n, accumulating the result. And the third uses reduce from the Factorials library. Factorials contains code that brings functional programming mechanisms to Python, hence the func part of the name. The reduce function implements a mechanism known as reduction, or sometimes folding. It takes a callable and an iterable. It calls the callable on the first 2 items of the iterable, stores the partial result, then calls the callable on the partial and the next item in the iterable. Sounds an awful lot like what was just written in the recursive version, right? To use reduce for a factorial, the callable is a lambda that takes 2 values and multiplies them together. The iterable is the numbers in the factorial specified here by range. And just in case range is empty, that OR clause makes sure that a value of 1 can be used instead. Let me open up the REPL and I'll try these out. Importing all 3 of them. Calling the recursive one. The loop. And finally, reduce. No surprises here, they all work. Let's see how they do performance-wise. The timeIt function is a helper that lets you time the execution of code. It's a little weird. It takes 2 strings, the first containing the code to execute and the second some setup. Timeit doesn't import anything from the namespace. So for our purposes, I need to use the setup to explicitly import the function being tested from the REPL. Let me show you how that works. The first argument is a string containing the call to recursive. The second argument is also a string, which imports recursive from the dunder main namespace. Don't worry too much if this feels like black magic. It kind of is. The third argument there is how many times to invoke the function and time the whole thing. Running the call to recursive 100,000 times took 0.021 seconds. Let me do this again with the looping version. A little slower, but not by much. Now, how about reduce? Half as fast. Guess this isn't the place to be using functional programming. You know what? All this may have been educational, but it was also a waste of time. Batteries are included. Python comes with a factorial function. Yep, it works. And it's almost 10 times faster. Most of the functions in the math module are written in compiled code under the hood, hence you get a big speed up. Next up, I'll show you how to use recursion to traverse tree data structures.